In this video, we are going to look at vector spaces. Okay, so we are going to define what vector spaces are, and then we are going to look at questions. Okay, where we'll be determining if a given space is a vector space or not. Okay, so for you to define what a vector space is, you need about 10 conditions. Okay, 5 of them will be under addition, and then 5 of them will be under multiplication. Okay, so I'm going to say let V be a set and R be a field. Okay, let V be a set and R be a field. Okay, then we are going to say that the set V, okay, is called a vector space. Okay, it's called a vector space over R if the following conditions are met. Okay, so I said we have 5 under addition, and then we have 5 under multiplication. So under addition, okay, we're going to say let vectors V, U, and W be a member of this space here, the V. So this one I should have written it like this. Okay, or we can call it a set. Let these vectors V, U, and W be a member of this set like this. Okay, then condition number 1 is that, okay, the condition number 1 is that V, this space here, the V here, has to be closed for it to be called a vector space. Okay, so what do we mean by has to be closed? It means when you get any two vectors in this set here, their sum should also be in this set. So we're going to say if V and U are a member of this set, okay, then U, V plus U should also be a member of this set. So this is the first condition, okay, of checking if something, of defining a vector space. This is the first condition that it must be satisfied. And then the second one is that all the vectors in here, their addition should be commutative. So meaning that U plus V should always be equal to what? V plus U. Okay. And then third is that all the vectors that you have in this set, okay, they should be associative. So meaning if I have U plus V plus W, this should be equal to U plus V and then plus W. Okay, so we are remaining with 2 under addition. Okay, so the fourth one is that there exists an element, okay, which we call the 0 element or the 0 vector. Okay, there exists a 0 vector in this set such that, okay, such that U plus 0 vector is just going to be equals to U, or 0 plus the U vector is just going to be equals to what? To U. So this 0 here is a vector, it's not a number. Okay, so there exists a 0 vector or the 0 element in this set such that U plus the 0 vector gives me back my U. All right, and then the last condition under addition, okay, I'm going to write it somewhere here in blue. So the last condition under addition is that there exists, okay, an element V, not an element, but a vector, okay? There exists a vector V, okay? Or let me just use another letter, okay? So I'll just say there exists a vector A, which is a member of this set, okay? Such that A plus, let me pick the vector U, the vector V here. A plus V should give me 0, or V plus A should give me what? 0. So those are the first 5 conditions, okay, for something to be defined as a vector space. Okay, so this is just under addition. Okay, so we're going to say if V is a set, okay, then it is called a vector space if the following conditions are obeyed under addition. Okay, so the definition will not end there. Okay, you have to go over the properties under multiplication as well. So I'm going to erase this. So these are under addition. Okay, so now if we go over multiplication, there are also about 5 conditions that must be met for something to be called a vector space. So the first one, we're going to say that, okay, for every, so for every alpha, which is which is a member of this field, okay, and for every u, which is a member of this set, okay, then we need to have alpha multiplied by u also be a part of this set. So this is just the closure rule, but under what? Multiplication. So meaning that if I have a scalar, which is a member of this field, and then I have a vector u, which is a member of this set, if I get their product, that product should also be a part of this set. Okay, so this is the first condition. And then the second condition, okay, is that if I have the scalar as a member of this vector field here, okay, so I'm representing that field by this arrow, okay, then if I have alpha as a member of this field, and then I have two vectors u and v as a part of this set, okay, then alpha, okay, alpha multiplied by u plus v should be equals to alpha u plus alpha v. Okay, all right, and then the third one that we consider is that if I have alpha and beta being scalars from this field, and then I have a vector u being a member of this set here, okay, then alpha plus beta multiplied by the u should be equals to, okay, should be equals to this u multiplied by what we have here. So it should be alpha u plus beta u. Okay, so that's the third one. And then the fourth one is just the existence of the identity element. Okay, so fourth one is that there exists. Okay, so there exists I'll just symbolize it as 1, but this is not 1. Okay, it's a vector. So there exists a vector 1, which is a member of this same set, such that if I multiply it with any other vector in that set, I get the vector back, such that IV is equals to what? To V. Okay, so, and then the last one is that when you have, the last one will be using these ones here, these conditions that are on number 3. So if I have alpha multiplied by beta multiplied by the vector V, then here I should just get alpha beta and then the vector V outside. Okay, so these are the 5 properties that must be satisfied under what? Multiplication. Okay, so for something to be a vector space, it has to satisfy those 5 under addition that we did earlier. And then it also has to satisfy these 5 that we've done under what? Multiplication. Then we're going to call that space or that set as a vector what? Space. Okay, so now when it comes to answering questions, okay, or proving that a given space is a vector space or not, okay, we only have to prove about 3 of these properties that we've written down. Okay, so the first one, we just have to prove that the 0 vector is part of that set. Okay, so the conditions that are needed are just 3. So we just have to prove that the 0 vector is contained. Okay, the 0 vector is contained in that set. Okay. And then 2, we have to prove the closure property. Okay. So the closure property is simply saying that what? If I have U and V being a member of this set, okay, then U plus V should also be a member of this set. All right, and then this closure property, we can also put it under scalar multiplication. So if I have a scalar here, alpha, being part of a certain field, let me say F, okay, and then I have U and V, okay, I have U and V being vectors which are part of this space, okay, then what it means that alpha multiplied by U plus V should also be in the space, okay, so we say here this is the the zero vector should be contained in that set, okay, and then the certain vector space that you've been given should obey the closure rule under multiplication, okay, and then the given space should also obey the closure rule, okay, under scalar multiplication, like that. Okay, so these are the 3 properties that we are going to be proving on the questions that we are going to be looking at. Okay, so now let's look at the questions. So we have question 6 here. So question 6, okay, they're saying which of the following subsets of VNR, where n is greater than or equal to 3, are vector spaces? Okay, so remember we just have to prove 3 properties. Okay, we just have to prove 3 properties. So A, we've been given the set where I have alpha 1, alpha 2, then all the way to alpha n, okay, such that alpha 1 plus alpha 2 plus alpha 3 is equals to 0. So the condition that we'll be working with here, it will be this condition here, okay? We have to make sure that whatever we do, whatever manipulations we do, we come back to this condition here, okay? So to prove that this is a vector space, we first check if the 0 vector is contained in this space. Okay, so we check the 0 vector. So how are we going to do that? We are going to say suppose the 0 vector was part of this set. Okay, suppose 0, 0, dot, 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 0 was part of this set here. So we can say that this set or this space is equal to V, like this. Okay, so suppose the 0 vector was a part of this. Okay, then what does it mean? Okay, what does it mean? So if the 0 vector is a part of this, then it means alpha 1 is 0, because there it's 0, alpha 2 is 0, and then wherever we are ending, which is alpha 3, is also 0. So here I'm going to say then alpha 1 is equals to alpha 2, which is equals to alpha 3, which is equals to what? To 0. Okay, so if alpha 1 is 0, alpha 2 is 0, alpha 3 is 0, okay, is this condition satisfied? Okay, so we see that alpha 1 plus alpha 2 plus alpha 3 will indeed be what? 0. Because this one is 0, this one is 0, this one is 0. So if we add them, they're all going to give us what? 0. Okay, so this will mean that indeed the 0 vector, okay, it will mean that the 0 vector, which is given by this, is a member of what? The space. So we have proved 1 property. Okay, so I said we just check 3 of them: the 0 vector, the closure rule under addition, and the closure rule under what? Scalar multiplication. So we have checked the first one. Okay, so the first one, yes, the 0 vector is part of this set. Okay, so now let's check scalar multiplication. Okay, so for scalar multiplication, we are going to say that, okay, let 2 vectors P and Q be a member of this space. Okay, then what does it mean? One of them, okay, one of them will be P is equals to, or just use alpha plus alpha 2. Oh, no. Alpha 1, comma, alpha 2, all the way to alpha n. Okay, so if P is a part of this, then P is that one. And then Q will be equals to, okay, so here now we can choose beta. So you can choose any letters there to represent your members of that vector up to beta n. So these are our two vectors that are there. So is P plus Q also a part of that set? Okay, so here I'm not just going to test the I'm not just going to test the closure rule under addition on its own. I'll put it together with the scalar multiplication. So I'm going to say also, okay, let n be a scalar, which is a real number like this. Okay, so now we want to prove that if I have P and Q a member of this vector space and n a member of the field R, okay, then n multiplied by P plus Q will also be a member of V. This is what we want to prove. Okay, so let's add them. So P plus Q will be equals to what? So we're just adding term by term. So this plus that one. Okay, so it will be alpha 1 plus what? Or maybe I do it in another way. Okay, this one, it will be a bit complicated. So we want to prove that n multiplied by P plus n is also a what? Is also in this vector space. So this one, if I distribute it, it's going to be np plus nq, right? Okay, so we want to check if this is a member of that. So n, okay, will be equals to alpha 1 plus alpha 2, okay, plus okay, oh, before I say that, let me say this. Okay, so if we are saying that P is given by this and Q is given by this, okay, for this vector P and for this vector Q to be a member of this set, then this condition here on top should be satisfied. So if I have my P like that, then it means that alpha 1 plus alpha 2 plus alpha 3 should be equals to 0. And then here, beta 1 plus beta 2 plus beta 3 should also be equals to what? To 0. So now I can prove this now. Okay, I can prove this now. So I'm going to say n multiplied by p, which is just np. So n multiplied by p, okay, but p satisfies this condition. So I'm going to write plus n and then q. So q also satisfies this condition. So it will be beta 1 plus beta 2 plus beta 3. Okay, but what do we see here? You have n, and then in the brackets here, this is just 0. So this will be 0 plus, and then okay, and then here to be n to also be 0 inside here. So I'll just get 0. Okay, and the 0 vector, at first we already proved that the 0 vector is a member of what? This set. So it means this answer here also be a member of this set. So what does that mean? It means that this is a member of this set. Okay, so since the 0 vector is a member of that set, and also n, okay, multiplied by p plus q is a member of this set, we would have proved our 2 or our 3 properties that we need to do in order to test if something is a vector space or not. Okay, so we're going to conclude that yes, this one on A is indeed a what? A vector space. Okay, let's look at B. Okay, so B, let's say our vector space is K. Okay, so K is equals to alpha 1, comma alpha 2, comma dot dot n, alpha n like that. Okay, okay, so alpha n such that alpha 1 plus alpha 2 plus alpha 3 is equals to 1. All right, so we want to prove, first of all, if the zero vector is part of this set. Okay, so we are checking for the what? For the zero vector. So for the zero vector, we are going to say suppose, okay, suppose 0, 0, dot, 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 all the way up to 0. Okay, suppose this zero vector is part of K. Then that would mean that alpha 1, alpha 2, all the alpha somethings here will just be zeros. So then alpha 1 is equals to alpha 2, which is equals to alpha 3, which is equals to alpha n, which is equals to what? To 0. Okay, so it means all the alphas here are what? Are 0. So if alpha 1 is 0, alpha 2 is 0, alpha 3 is 0, is this condition met? Okay, it turns out that it won't, because it will be 0 plus 0 plus 0 is equals to 1. And we see that this is a contradiction. Okay, so this would mean that the zero vector is actually not a member of this space K. So if we just found that one of the condition fails, then we're going to conclude that what we have here on B is not a vector field. Okay, it's not a vector field. It's not a vector space. Okay, so now let's look at D. Okay, so you can try out C. Let's look at D. So D, I'm going to say let my vector space be equals to this. And then we have 1 plus alpha 2, then alpha 2 dot 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 until alpha n. So here we don't have alpha 1 anywhere. Okay, so the first thing is to prove if the zero vector is there. So we're going to say suppose, okay, suppose 0, 0, dot 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 0 is a member of this V. Okay, then that would mean that, okay, this part is 0. Even this part is 0, even this part is 0. Okay, that's what it would mean. So it will mean that 1 plus alpha is equals to alpha 2 is equals to alpha n. But here we see a contradiction because this one to be 1 plus. Okay, so this is the alpha 2 here. So alpha 2 will be 0 is equals to 0 is equals to 0, the alpha n. But you see that we have a 1 here. So 1 will never be equals to 0. So it means the 0 vector here is not a member of what? Of this vector space V. So if the zero vector is not there, then it won't be the vector space. Okay, so that one won't be a vector space. All right, so that one won't be a vector space, and then let's try to check. Okay, let's try to check E. Okay, so let V be equals to alpha 1, alpha 2, dot dot alpha n, such that the modulus of alpha 1 is actually greater than 0. Okay, so let's try to prove this one. Okay, so the first thing is always to check if the zero vector is there. So we're going to say suppose 0, 0, dot, 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 comma 0 is a member of this vector field. Okay, then that would mean what? That would mean that x1, alpha 1 is equals to alpha 2, which will be equals to dot, 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 alpha n is equals to 0. Okay, so all the alpha somethings will be equals to 0 if this here is a member of this space. Okay, so now is this condition satisfied? So if I get alpha 1, which is just 0, so it will be alpha 1, which is 0, the modulus should be greater than 0. But this is not true because the modulus of 0 is just 0 and 0 is not greater than 0. So this is a false. So it means the zero vector is not a part of this vector field. So if it's not a part of that vector field, then we are going to say that what we have is not a what? The vector field. Okay, so that's what we have there. That's what we have there. Okay, so you can try out this F and this C. Okay, to see that if you've understood what I've said here. Otherwise, let's look at the last question here. Okay, so it's still on vector spaces. So here they're saying which of the following subsets are subspaces of this. So for something to be a subspace, then it has to obey the properties of a vector space. Okay, so how do we prove them? We just prove that whatever we've been given here is a vector space. That's all. Then we would have proved that they are subspaces. Okay, so the first thing, as usual, is just checking if the zero vector is there, and then checking if we get any two vectors, okay, their sum will also be a vector. Their sum will also be in that vector space, okay, and then we also check the scalar multiplication. So we're going to combine the closure rule of the sum and the scalar multiplication. Okay, so now let's say this set here be equals to W. So now here we've been given in terms of a matrix where A is equals to B. Okay, so let's check if the zero vector is there. So the zero vector in this case now will be 0, 0, 0, 0. Okay, so we're going to say suppose 0, 0, 0, 0 is a member of W. Okay, then that would mean that A is equals to B is equals to C is equals to D, which is equals to 0. Okay, so now is this condition satisfied? So if A is equals to B is equals to 0, then A is equals to B is equals to 0 is satisfied. Okay, so therefore the zero vector, this one, the one I'm representing as 0 there now, is a member of this set. Okay, so we've checked the zero vector, it has passed. So now let's check if the scalar uh, if the addition and the scalar multiplication will also be a part of this set here that we have. Okay, remember our condition, A has to be equals to B. In short, the element that is there and the element that should be there should be equal. So I'm going to say let P and Q be a member of this set. Okay, so if P and Q are a member of this set, then I can represent P as, okay, I'm just going to say A1, B1, C1, D1, and then Q, I want to say this is A2, B2, C2, D2. So this is what I'm going to say. And then I'm also going to say that let K be a scalar in the field R. So I want to prove, okay, I want to prove that KP plus Q is also a member of what? This set W. Okay, so if this set is a member of this set here, then it means A is equals to B. So here it will mean A1 is equals to B1. Here to mean A2 is equals to what? To B2. So I want to prove that this one here is true. Okay, so how do we do that? We're going to say K P plus Q is equals to K, the P is A1, okay, B1, and then C1, D1, plus the Q, which is A2, plus B2, C2, D2. So this is what we have. So let's check that one to see if to be a member of this. Okay, so we are going to say that let's add. Okay, let's add this and this. Okay, but before we add, we have to multiply with this k with this. So what we get there will be k like that, k c1, k d1, and then plus a2 b2, C2, D2. So if we add this, what are we going to get? We're going to get K A1 plus A2 plus K B1 plus B2. This here will be K C1. Okay, so K C1 plus C2, and then K D1 plus D2. So that is what we have. So now, is this a member of this set here? Okay, remember the condition. For you to be a member of this set, then A has to be equals to B. So these two have to be equal. So are those two equal? That's what we want to prove. Okay, so are those two equal? Okay, remember we said A1 is equals to B1, B2 is equals to A2. So K A1 plus A2 is equals to K B1 plus B2. So this is true. Why? Because what I have here and what I have there is the same. Remember, A1 is equals to B1. So this one and this one are equal, and they are being multiplied by K. So this expression is equal. And then on the other side, A2 is equals to B2. We can see A2 is equals to B2. So it means the right and the left are equal. Okay. So since the right and the left are equal, we're going to say yes. Okay. The closure rule passes there. So we're going to say that yes, this W, okay, is a subspace. Or we can say it's a what? A vector space. That's all. Okay, let's look at B, and then I'll leave C for you to try. Okay, so B, we're going to say let L be equals to this set such that A plus B is equals to 1. So the first things to check is the zero vector. Okay, so is the zero vector a part of that? That's what we want to check at first. Okay, so we're going to say suppose 0, 0, 0, 0 is a member of L. Okay, so this would mean what? It will mean that A is equals to B, which will be equals to C, which will be equals to D, which will be equals to 0, because I can see all zeros there. Okay, so does this satisfy this condition? Okay, so A plus B is equals to 1, but here A is 0, B is 0. So this will be 0 plus 0, which is equals to 1. So it will just be 0 is not equal to 1. Okay, so meaning this zero vector or zero matrix is not a part of this. So we're going to say 0 is not a part of L. Okay, hence L is not a subspace, or it's not a what? It's not a vector space. All right, so for today we end here. Okay, but I have an exercise that I would like you to try. So on the website, there are written solutions to all these questions. Okay, they're already there. So whatever answers you find, okay, to this question here, what was the other one? This question and this question. And then I also have another question here, a bonus one. You should try it out, this one here. The solutions are there on the website. So once you try them out, and then you try to check with the correct solutions on the website. All right, so have a blessed night.